Okay, in today's class we'll be talking about SNR calculation of a DSB SC signal which is being received by a super heterodyne receiver. So let me just write it down over here. SNR calculation of a DSB SC signal in the presence of additive white Gaussian noise at the output of a super heterodyne receiver. So that's what it's all about. So as the title itself indicates, we are going to receive a DSB SC signal using a super heterodyne receiver, and the noise that is going to accompany our DSB SC signal is nothing but additive white Gaussian noise. So let us start with a block diagram. Now coming to this block diagram, we'll only consider those blocks of a super heterodyne receiver that are going to be useful for us in this derivation. There are many blocks which are not actually necessary, or they take a part in the super heterodyne, I beg your pardon, there are many blocks in the super heterodyne receiver which are not actually going to take part in this SNR calculation. So we are simply going to neglect them and we are going to consider the other blocks. Alright, so let me just write it down. This is the carrier filter and the corresponding transfer function is hc of f, and this is the baseband filter and the corresponding transfer function is hb of f. Now this is nothing but a multiplier, and with the help of this multiplier we are going to perform a synchronous demodulation of the DSB SC signal. So let us suppose the local carrier that we are using in the receiver is cos 2 pi fct. Alright, so the blocks which are necessary for us in the derivation of the SNR with respect to a DSB SC signal are the carrier filter, obviously the detector in which we are making use of the multiplier, and the baseband filter. Now let me just also show you the respective plots or the frequency responses with respect to the carrier filter and also the baseband filter. Now coming to the carrier filter, it is well known that the carrier filter bandwidth is same as that of the bandwidth of the transmitted signal. So because of that reason, the carrier filter bandwidth will be twice of FM, because the DSB SC signal has a bandwidth of twice of FM. So let me just write down the transfer function exists in the interval fc minus fm to fc plus fm, where the center frequency is nothing but fc. On a similar note, towards the negative end, it extends from minus fc plus fm to minus fc minus fm, again the center frequency being minus fc, and the magnitude is equal to 1. So you can simply say that we are considering an ideal carrier filter, okay, which as you all know is an ideal band pass filter. Alright, now let us have a look at the transfer function or the frequency response of the baseband filter. Now the baseband filter is supposed to have a bandwidth which is equal to the bandwidth of the message or the baseband signal. Now, assuming that we are going with a sinusoidal message signal whose highest spectral component is FM, I can simply say that the baseband filter transfer function is going to extend, or it will be non-zero in the interval from 0 to FM, where FM is the highest spectral component of our message signal, and obviously on the other side to minus FM, and the magnitude is again same as 1. So it should be obvious to you that the baseband filter is nothing but an ideal low pass filter. Alright, so let us also simply mention the input to the carrier filter. It is nothing but a DSB SC signal, and besides this DSB SC signal we have additive white Gaussian noise, alright, with the power spectral density equal to Gn, which is obviously eta by 2. Alright, let me also denote the DSB SC signal as Si of t. Now at the carrier filter output, the DSB SC signal will get modified into S1 of t, and on a similar note, at the carrier filter output, the power spectral density of noise will change to Gn1, and at the multiplier output, the DSB SC input will modify into S2 of t, and on a similar note, the PSD of noise will become Gn2. And at the output of the baseband filter, I'll simply consider the signal component to be S0 of t and the power spectral density of noise to be Gn0. So this is the block diagram corresponding to our SNR calculations. So let us first of all start with the power calculation of the signal. Okay, so step 1 is calculation of signal power. Now calculation of signal power, so let's consider the wanted signal Si of t such that it is equal to √2 times A cos 2 pi fmt and cos 2 pi fct. So let this be equation 1. So this is our DSB SC signal. Okay, now mind you, we need to remember that assuming a single tone sinusoid as the message, the DSB SC signal becomes equal to signal in equation 1. So the point is very simple. Equation 1 will be a DSB SC signal provided the message signal is a single tone sinusoid. Now, considering equation 1, so we have that SI of t is equal to root 2 a cos 2 pi fmt to cos 2 pi fct. Let SI be the average power of SI of t. Then from equation 1 we have SI to be equal to limit t tends to infinity 1 by t integral over t SI square of t dt. So we very well know that this is the formula for calculating average power, and it's simply be going to equal to a square by 2. Alright, it should be obvious to you how we arrived at a square by 2. So the input signal power is simply a square by 2. So let me just write it down. Let this be equation 2. So now let us calculate the power of the input signal that is available at the output of the receiver. Now let us see that at the output of carrier filter, the signal component is S2 of t. We already know that the signal component at the output of the carrier filter, beg your pardon, it is S1 of t. Let me just make the correction. Okay, so S1 of t. Now if we just go back and see, S1 of t is the signal available at the carrier filter, and we obtain S1 by processing Si of t. So now we have a DSB SC signal. Si of t is basically a DSB SC signal, and it extends from Fc minus Fm to Fc plus Fm, and the magnitude is 1. Alright, so it is going to pass through the carrier filter unaltered. I hope everything is clear so far. It is going to, the Si of t is going to pass through the carrier filter unaltered, because the carrier filter frequency response extend in the same interval in which Si of t is basically present, and the magnitude of the carrier filter is equal to unity. So Si of t is simply B is equal to S1 of t. So let this be equation 3. Now the signal at the multiplier output Yes, the signal at the multiplier output is simply S2 of t, and this S2 of t is nothing but S1 of t times cos 2 pi fct. So let me just write down, at the output of the multiplier I have the signal as S2 of t, which is equal to S1 of t cos 2 pi fct, which is equal to Si of t cos 2 pi fct. Now substituting Si of t from equation 1, I am going to get that root 2 times a cos 2 pi fmt into cos 2 pi fct whole multiplied by cos 2 pi fct. So we are simply performing synchronous modulation, and the output is going to be root 2 by 2 a cos of yes 2 pi fc minus fc into t plus cos of 2 pi fc plus fc into t whole multiplied by cos 2 pi fmt. Simply made use of the formula twice of cos A cos B. So over here I am going to get 1 by root 2 times A into cos 2 pi fmt plus cos 2 pi fmt into cos of 2 pi into 2fc times t. So this is going to be my output at the multiplier. So let me just call it as equation 4. Okay, now the next step is to calculate the signal output at baseband filter